Yes, so the topic is control, privacy, security in the cloud, and hopefully you will be clear as we go along what I mean by these things. So first I'd like to tell you a little bit about what control is all about. So this is an introductory slide about control engineering. So basically you can think of control as the science or art of making systems behave in a manner we would like them to behave in. So what the system could be something we build, or it could be a biological system. So basically it's the art of changing behavior in a systematic fashion. And a very common, a powerful principle to achieve this is using feedback. And feedback, at least in our field, is often illustrated by means of a diagram, what we call a block diagram. And the object we would like to control, or whose behavior we would like to change, is what we call a plant. So in the old days, a plant could, for instance, be a steam engine in a factory. So go back to the 19th century. So what would you like to control there? Well, for instance, we could imagine that the revolution, the speed of revolution of the steam engine is something we would like to be constant over time. So even though the production changes over time, as you increase the load, the speed might go down of the engine. So somehow we would like to have some sort of automatic mechanism that adjusts the speed of the steam engine as the load changes. And control is about, this is a typical example of a control problem. And how do you achieve that by means of feedback? Well, there's something I call is here. By that I mean something we measure, something we would like to change. In this case, with a steam engine, it's actually then the speed of revolution. So if you follow now the arrow here backwards, we subtract that measurement from some reference point I call should. It's a target value. Let's say that is the actual speed we would like the engine to rotate with. So the difference here now is basically a measure of a misfit, if you like, how far away we are from the target speed of the steam engine. So this now is being fed into something, a mechanism we call a controller. I will come into what this could be. And that controller now should make some wise decisions on how to change the plant to increase or decrease its speed. For instance, by changing a valve to let in more or less steam into the engine. So what could a controller be like? Well, back in the 19th century, it was often something like this. It's a centrifugal governor. It's basically an axis here which rotates with the same speed as the steam engine. If it goes too quickly, the centrifugal force will pull out the arms, and it will basically close a valve and decrease the amount of steam going into the engine. It will slow down. And conversely, if it's moving too slowly, the arms will go in and open up the valve and let in more steam, and the speed will increase. So this is one example of an automatic control system using feedback that will regulate the speed. So this principle is very powerful, and it's being implemented in many systems today. So here are some examples. An airplane. Most of these contain lots of these type of feedback control loops to assist the pilot with flying the planes. Robots, how do you make a robot follow a trajectory in a factory to build, to manufacture products, for instance? And here's another picture. It's a water tank, which most students at KTH who take control engineering, they're spend quite a number of hours sitting with this process, trying to learn the principle of feedback control. Now, of course, the controller in our labs is no longer something like this. It's not a centrifugal governor. Instead, it is often an embedded computer, a small computer, which actually collects these measurements and perform a computation, and then decides how it should change the behavior. But the principle of feedback is still there in all of these systems. So, what is new now? What's new with these type of systems? Well, these feedback loops are nowadays moving into the cloud, and that was one of my keywords of this talk. So what do I mean by the cloud here? Well, basically think about any large-scale communication network we have around us. For instance, think of the internet. So in this previous example, the controller and the plant was sitting next to each other, basically in the same room. Well, nowadays, there's no real reason to put the controller physically next to the plant. Why not put it in the cloud? It could equally well be sitting in a server on the other side of the world. It's actually a much more flexible solution. And it also helps us to solve quite many more complicated control problems. For instance, if here you see 3 different plants, suppose now that these 3 plants, you would like to coordinate them in some manner. Then it's actually much more convenient if their controllings are sitting in a place where it's easy for them to talk to one another and share information. And that could very well be in the cloud. So one example where this is quite useful is modern transportation networks. So think now of every plant here of a car, an autonomous car, which you would like to control the speed on the road. 3 of them would form a platoon or a vehicle fleet, and maybe you would like these fleet, you want to control this fleet, and then it would be quite useful to have these controllers sitting next to each other. They could actually optimize the performance much more. So this is one example of where this is useful. Power transmission is another case where every plant here would be a power plant, and the controller now would decide whether it should increase or decrease the production. And the cloud now can help you to make a wise readjustment of production if, for instance, the wind starts to blow in a certain region, so maybe you should increase production there, whereas you should decrease it in another place. But it could also be useful in factory environment where many control systems now can start to talk to one another using the cloud technology. So this is what I mean by control over the cloud. Some of the traditional control challenges that we've been caring about for the last century are listed here. Stability, performance, robustness, and safety. So those all are still relevant. Let me just briefly go through them and tell you a little bit about what they are. So stability basically means that this feedback loop here is stable, that every state are not going into some infinite state. For instance, in the steam engine, an infinite state would mean that the system explodes. So stability is something we always want in a feedback system. Performance means that you would like the is value to follow the should value in a fast manner, fast enough. So that's a performance measure. Robustness is always an important issue because all of our systems we build are always subjected to random fluctuations in their environment. For instance, there is external disturbances affecting the plant and the controller, and still you would like the feedback system to be able to operate under these uncertain environment. That's the robustness. Finally, safety. It's basically making sure that the states of the plant are always safe. So in the case of the car fleet, for instance, that the cars never come too close to one another under any circumstance. So these are all classic challenges that we've been working with. Now, let's now think about what happens if we move this feedback loop out into the cloud. Well, there are some new issues arising, and I've listed 3 of them here: security, privacy, and learning. And today I will mostly focus on security and privacy, and in particular I will give you 2 examples of 2 projects we're working on where we address these issues. So let me say a little bit first what these are. So security, what do I mean by that? Well, if we now put the controllers inside a cloud, what if there are, let's say, hostile or malicious agents in that cloud, hackers, who are able now to put in malware or being able to affect signals here? Could they affect the physical plants down here? Yes, the answer is of course yes. So how do we now design? We still want to achieve these criteria up here. So how do we achieve those while thinking about the possibility of IT attacks in the clouds? Is that possible, and how do we do that? Privacy is another interesting problem. So from this figure now, the client here, what the client or the plant is doing, he's pushing his information up into the cloud, into a controller, and in reply he gets some wise decisions on how he should adjust his behavior. Well, if you do that, you notice that the controllers may very well start to sharing some of that information with neighbors. And maybe you as a client down here are not really aware that your information is actually being fed up to other systems. So that might be a conflict of interest here. So how do you make sure that you get good control performance down here while you still have some sort of personal integrity, say? Depending, of course, of the systems you're thinking about. this may be more or less relevant. But I will give you an example where this is very relevant, just in a few slides. So let's first to look at an example of security. So here is the smart grid. So I think the other speakers have talked about the smart grid in this lecture series. So I will just briefly go through what this system is about. But it's a beautiful example of a control system where you need lots of feedback control, and you often rely on communication networks. So every plant here now is a power plant. It could be a nuclear power plant, a coal power plant, water power plant, photovoltaic, solar panels. It could be cars that have batteries where you can put in or take out energy and put into the grid. They all share information over communication networks to control centers. They can be big control centers, national level control centers, but it could also be smaller ones, maybe one in each city. And in these control centers, you make decisions on the production levels that the plants should follow and send them back to the plants. So there are lots and lots of these feedback loops being closed over these communication networks now. So what if now I put in some evil faces here? This should now illustrate the possibility of hostile attacks. Suppose now that somebody comes in here in the system and are able to manipulate signals or softwares. How do we make sure that this system still works, or at least doesn't, the performance kind of gracefully goes down, at least when there is an attack, so that we still have some sort of good performance in the system? And this is exactly what some of our current research is about, trying to achieve such goals. And there are many different problems. Here I would like to just mention one we call anomaly detection metrics. So what is that? So an anomaly detector is basically a piece of software where you collect lots of these measurements and you try to decide whether these data are normal or if there is some indication in the data that something bad is happening. There's a fault in the system or there's an attack going on. So these anomaly detectors are quite complicated systems themselves, and there may be many ways to build them, and there may be many parameters to tune in these detectors. So the question is, how do you even compare which one is better for a certain system? And this is one of the research objectives we have here. And here, for instance, we compute trade-off curves for every detector, which are basically tell us which one is better. So just to briefly go through what we're looking at. So on this axis here, there is what we call the expected time between false alarms. So every detector will every now and then give a false alarm. There's random fluctuation in the environment, and so there will be false alarms. If there's too many of them, of course, you will not trust the detector and you will turn it off. So you want something large here. There should be a long time between the average false alarm. And you can achieve that typically by increasing some thresholds in the detector. On the other hand, when you do that, you also leave some room for an attacker to attack the system without causing damage. So the question is, how much room do you give? When you increase the average expected time between false alarms, how much room do you give to the attacker to cause physical damage? And that's what you have on this axis. So here are then two different detectors, and in this case, detector 2 is the better one, because if you take one expected time between false alarms, you see that detector 2 leaves much less room for an attacker. So in this case, detector 2 would be the better choice. So we're working on basically trying to compute such curves for concrete systems and how to use this information then to tune parameters. So this is one of our ongoing projects. Then I'd like to say something about the privacy issue, which was the second new challenge in control over the cloud. And what you're looking at here is basically the energy consumption pattern of a household. So on the x-axis, you basically have the time of day, so it's 24 hours, and on the y-axis, you have the power consumption. So for now, you can forget about the colors. Just look at the profile here. And it actually reveals quite a lot about the person living in that house. You should be aware that this is the type of data that your smart electricity meter could take. It basically can measure all the time how much power consumption there is in the house. It could transmit that to the smart the smart grid, and the smart grid could use this information to set prices and change the production. So it would be quite useful for the grid to know this information. But as I said earlier, this also contains information about the person living in the house. So here, for instance, you see that the person probably wakes up around 6, comes home for lunch around 12, home again around 6 p.m. here. Furthermore, a lot of the house appliances we have, they have a very distinct energy use pattern. And that is what the colors are about. So when you turn on a device, their energy profile is quite distinct, and a person who knows this could often guess, or you can use a computer to help you to guess what type of devices are being used, and that's what the colors are showing here. So the green color here basically shows this pattern corresponds very well to a dishwasher. So then you know that the person probably turned on the dishwasher after lunch. Here you can see that the person turned on the washing machine and then the dryer, for instance. And you could even see things like the TV is on, and you could even try to correlate this and see what type of TV program persons are watching. So that is may or may not be a concern to you, that when you participate in this smart grid, that you're actually leaking a lot of information about your personal life. So how can we convince people to participate in these systems while giving away this type of data? That is one problem we're working on right now. One way to achieve this is to actually use an energy buffer, a battery. And this scenario maybe is not so unlikely because in the smart grid there are already suggestions that every house or large house should have a battery where you can store green energies. Let's say the sun shines, then you charge your battery, and then when you come home and the sun doesn't shine, then you can use it. So you save green energy. So there's always the talk about having batteries. Now what we're thinking about, well, we could use some of that energy to buy us privacy. And the idea is quite simple. Suppose you come home at 6 o'clock and you turn on the light. So instead of taking that energy from the grid and signal to the world at your home, you take it from the battery, your private energy storage, and then of course you don't leak that information. Of course you need to charge the battery to compensate for this at some time, but basically by doing smart charging and discharging you could decorrelate your personal behavior with your electricity signal, and that becomes an interesting control problem because now we have many objectives. We want to control the batteries so that we have some privacy. We also want to save, we want to use green energy, but we also don't want to use the battery too much because it will be wear and tearing on the battery, which is a costly thing. So what you're looking at here is it's again a metric where we try to compare different types of control strategies. I will not go into too much into detail, but basically the F-score here is a measure of somebody who's trying to guess whether the fridge is on and off. And without a battery, the score is 0.5, which is 0.7, sorry, which is pretty high. So it's quite easy to identify the fridge from the data. Now, if you have a battery which size is 0.5 kilowatt hours, this is a quite large drop, actually. And then you can see here that the bigger battery you have, of course, you get more and more privacy. And then you can compare, depending on the energy profile of the device, this becomes harder or easier. But again, this is a type of metric we're using to try to compare different strategies when we do our control design. So these were my two examples of security, privacy in the control in the cloud. And I hope you also learned a little bit about control engineering and what type of problems we're working on right now. And by that, I would like to end and thank you all for your attention. Thank you very much.